All right, so far we've been talking about tangent lines to the graph of a function. And I want you to think about what key property that graphs of functions have. See if you can think of it. They pass the vertical line test, right? That's the key defining property of the graph of a true function. If you're not a function, you don't pass the vertical line test. If you are a function, you do pass the vertical line test. And so our goal today is to learn how to compute tangent lines to other curves. And when I say other curves, I mean non-functions, things that don't pass the vertical line test. And so this technique is going to be called implicit differentiation. So I'm not going to try to answer all the questions that might pop up. I do want to give you a sense of what we're doing, and I'm going to show you how to do it. There is some question of why this works, and I'm not going to cover all of that here in these videos. So let's look at the classic example, x squared plus y squared equals 1. Hopefully you recognize this equation. If you don't, you need to jot it down and make a point to memorize this. This is the unit circle, right? X squared plus y squared is 1. Classic curve. Here it is. Got it all ready to go. So a couple of observations about this equation. This thing is not a function. This is just an equation. The equation defines a curve. You can draw the curve, but it's not a function. Why? Because it fails the vertical line test, right? Here's a vertical line intersecting the curve in two places. However, this curve still has a unique tangent line at any point on the graph. Let's make sure that that's clear to us. So pick a point right here and you can see there's the tangent line, or right there, and there's the tangent line, or right here, and here's the tangent line. So even though our techniques don't seem to work, right, we've learned how to take derivatives of functions. What we've been finding is still here. We just don't know how to find it. And so we're going to be able to find it, and we're going to use the same notation. So let's write down that we'll use the same notation as before, and the notation is like y prime, or change in y over change in x, so dy dx. This is going to refer to the slope of the tangent line. All right, it's just the derivative when we use that notation. A couple of things that I want to point out as well is that y is not a function of x. When you solve for y, you get y squared is 1 minus x squared. So y is plus or minus the square root of 1 minus x squared. There's actually two functions in play, right? The positive square root is the top of the circle. That is a function by itself. It does pass the vertical line test. Negative the square root gives you the bottom half, and that's a function as well. So y is not explicitly a function of x, but in this context we say y is implicitly a function of x. And so I'll put an arrow over there. Okay. So what's the key idea here? I want to be able to take the derivative. I want to find dy dx. How do I do that? So what you do is you assume that y is actually a function of x. You just assume that it is a function of x, and then use the chain rule. And I'm going to show you exactly how to do this. So what I want you to see is when I look at x squared plus y squared equals 1, then I want you to imagine that y is f of x. So I'm going to write down x squared plus f of x squared equals 1. I'm not usually going to write it this way, but this helps me to see it. Now I'm going to take derivatives like I normally would. So the derivative of x squared, you know, is 2x, plus the derivative of a function squared by the chain rule, you know, is 2 f of x times the derivative of the inside, which is f prime, equals, that's the derivative of this, is right here, and then the derivative of 1 is 0. And now you could solve for f prime. You could say, okay, so in this case, I can see that f prime of x is going to be 2x over 2 f of x. Y is f of x, right? And so you would write this as x over y, except I needed a negative up there. There we go, negative x over y. Okay, so that's how you do it. That's it. We typically won't actually replace the y with f of x. Let me show you how we're going to do it. We're going to write x squared plus y squared equals 1. But in our minds, when we're doing these kind of problems, we're remembering that we're viewing y as a function of x implicitly. And so whenever I take a derivative of a y squared, I need to view it as a chain rule. So here we go. I'm going to take the derivative of x squared. I get 2x, done, nothing to it. X's are fine. Plus the derivative of 2y, I'm going to get 2y dy dx equals 1. And then just like before, it's exactly the same math. I'm just using different symbols. Just like before, I solved for dy dx. I said equals 1. You guys know better than that. The derivative of 1 is 0. Whoops. Dy dx equals negative x over y. So that's the claim. Now, let's actually take this formula and go up. We're saying that the slope of the tangent line at any point x, y is negative x over y. Don't be alarmed that your formula has y's involved. It has to have y's involved because when you pick an x, there's not a unique y associated. So when you want to talk about the slope of the tangent line to the circle, you actually are talking about that slope at a specific x, y pair. So let me show you a couple of things and then we'll erase this up here. So we're claiming that's the derivative at any point. So let's think about this point right here. This is the point x is 0, y is 1, and so the slope would be 0 over 1, which is slope 0. So that worked. What about right here on the line y equals x? So y equals x. When y is x, our slope is going to spit out negative 1, and that's the slope, right? You can see the slope of the tangent line is negative 1. What about right here? We get a vertical line. This is the point, what? X is 1, y is 0. And you can see that in that case, I'm just dividing this thing. I get negative 1 over 0, right? Which is blowing up to infinity. It's undefined, and that's that vertical line there. So anyway, you can see these slopes playing out as you pick a pair. You have to actually pick a pair, xy, a point xy on the curve. You plug it into this formula, and that spits out the actual slope of the tangent line at that point. All right, well, let's stop here, and then in the next video, we'll do some more complicated examples. But you've seen the tricks at this point.